So, welcome everybody. My name is Per and I work in the Java Core Library team at Oracle. And today I'm going to talk a little bit about StableValue and SegmentMapper. Now, we haven't talked about StableValue or the segment mapper before. This is the first time we do a presentation because we have worked, Mauricio and I, together and kind of refine the concept over the past 2 years, actually. And in fact, I think just less than an hour ago, I submitted the StableValue JEP. So we will see when that will end up in your favorite JDK. So the agenda today is to talk about stable values, which is something that is called deferred immutability. And it will give you significant performance gains under certain circumstances and less verbose code. So that's kind of two things at the same time. Then I'm going to talk about the FFM SegmentMapper API. And the FFM is the Foreign Function and Memory API, which was first publicly released and finalized in Java 22. And this is kind of an extension, an improvement of that. And it's a kind of a flat memory marshalling capability where you can view flat memory as structured data, which is composable and succinct and give you much less verbose code than before, while retaining the same performance as you would have hand-coded all these kind of adapters. I'm going to spend most of the presentation today at StableValue because that's closer to be shipped. So we will see how much time we will have. So I'm going to talk about the motivation. What kind of problem are we trying to solve here? A little bit of what is StableValue, and then I'll do some demos, and then we'll show some benchmarks, and then we can open up for feedback from you. So this is my copy of Effective Java at home, and in item 7 we can read minimize mutability. And that's of course good. We want to have everything, final declared. So this is the JEP that are going to provide us with that capability without sacrificing flexibility of initialization. Okay, I'm going to fiddle around a bit here and jump over to code. Let's see here. So there we are. Okay, so this is a very typical component, you can say. So we have I have this scary whirlwind up there. So let's see. I hope that will disappear in a while. So we have the order controller up there, and this is very typical. I have a logger, which I initiate. I create a logger, and then I can use that logger in my component. And this is all great, but it has some disadvantages because it's slow when you start up. Usually, creating a logger entails to go out and pick up some XML file, and maybe you have a kind of log rotation. You create directories, and this all takes a long time to do. So therefore, I've given this a turtle up here because it's slow. It's performant once you have initialized it, but otherwise it's slow. So, and unfortunately, there is something going on here. Don't know what it is. So maybe I should, start all over here. Ignore. Okay, hopefully I will bounce back again. As you can see, I have a lot of things going on. Sorry for that. Anyway, here we are again. So let's go over here and, wow, we bounced back. Perfect. So that's a very typical pattern. I think you will write this kind of code without blinking. This is usual stuff. And imagine that we have an application. Why is it not working? There we are, with an application with perhaps 3 components or 10 components or maybe 100 components. And each of those components has a logger in itself. So therefore, I've given this 6 turtles because now you have to create an order controller, and that order controller has to create a logger. Then we have to create a product repository with a logger and a user servers with a logger. So that's very slow indeed when you want to start everything up. So what we can do is that we can move away from a final field and have a mutable field, which is not final. And then we kind of sadly has to go via this new invariant here. We have to refer to logger via a method. So this method would check whether or not we have initialized the logger, And if not, we initialize it and then just return it. And while this might look good from on the surface, it's really catastrophic. It's catastrophic in a way that it's slow, because this will not be constant anymore. But furthermore, it's like if you have a multi-threaded operation, you can create several loggers, and you can have very subtle concurrency issues with this solution. So it's slow and bad. You can, of course, serialize your access to the get logger by marking this as a synchronized method. This will solve the issues, but it will be even slower. So this is not good. And still, even still, you can make some improvements here. You can use something called the double check locking idiom, which is like you check the value and see if it's null. If it's not null, then you know it's been initialized. But if it was observed as null, you must synchronize and check it again, because another thread might have updated. And then once you check the value inside the lock, then you know whether or not it's set. And if it's not set, you create it. Otherwise, you just return the value. So this, I think this is kind of a clumsy code. And it also introduced this very subtle thing up here. Unless you declare this variable here as volatile, you will have bugs in your code that it's not so apparent why you have them. This will kind of make it possible for a partially initialized object to be seen by other threads. So this is very brittle, and therefore I've given it like a -1 and still a turtle, because we are not able to constant fold this field, because the VM is not able to reason about constantness. There's no way for the compiler to see that this will only change once, and so it's not a trusted field. And you can imagine if we have several loggers, or want to have something with an array that's protected, we must have several immutable exclusions, and we have an array, but you can't declare an array as volatile, because volatile only refers to the actual reference to the array and not the element as such. So therefore, we must do all the memory semantics, whether it's volatile or plain semantics, manually. So the first time I go in here, I have to do a volatile access, because I want to establish the happens before relation between any writers. Then, if it's observed to be 0, I go into the synchronized, which is using this kind of per element synchronized mutex. And then I can do a plain read here, because now I'm synchronized, and I'm synchronized on the same object that actually updates the value. But then again, when I update the value, I must use volatile semantics, because if another thread goes in, they use also a corresponding volatile access. So this becomes very error prone, and therefore I've given it not only a turtle but a ghost up here. I know it's own Halloween, but there we are. So I don't think the double check locking idiom is any good. There is another way, of course. You can leverage the static initializer idiom that is built on Java's class loader, lazy class loading. And you can say that here I have a class with a variable, and it's only when I refer to this holder that this will actually be initialized. And this guarantees actually that the logger is only created once, even in a multi-threaded environment. But unfortunately, this is only valid for static fields. I think you remember that in our example, this wasn't a static field, it was an instance field. And so this will also, render an elephant, because now you have to carry the weight of a separate control class here. You have to hold all that knowledge about this class in your code. So still nothing good. So let's see what we can do about the situation. Well, there's still something we can do. We can use a concurrent hash map to store things, and that's actually quite nice if you look at it from a code perspective. You can say that I have a map from class to logger, which I only intend to ever fill with one single component or one logger, and then I can return the value of a logger, but if it's not computed, I will compute it, and here's the recipe for that. So while that sounds nice, it's both an elephant and a turtle, because concurrent hash map is very, extensive. You have an array of elements, and each element is an entry, and each entry has a key and a value, and so on. So this would create a lot of overhead in your memory. Okay, so enter StableValue. So instead of having a private final logger, or we have a mutable logger, we have something in between. We have a stable value of type logger. So we say that the stable value is something that has an underlying data which is not initialized yet. And you can't observe that data unless it's there. And it's very similar to the map example I just showed. There is a compute if unset. So when you create it, it's unset. So we say that return the value of a logger, but if it's unset, here is the recipe for actually making it. And stable value will actually guarantee that this lambda here that are given will be only invoked once, even in a multi-threaded environment. And not the least, the JVM, because we made some changes to the UVM, stable value is treated in a special way. So the VM actually knows that this value can only be updated at most once. So if it has been updated, it can constant fold this value, meaning that it just treats it like a constant. So we get the best of both worlds. We get flexible initialization and we get performance at the same time. And you can only imagine what that will give us when we go to the kind of application level where before, we have this kind of upfront creation, but now we can say that these are also stable values. So we have a stable value of an order controller, stable value of product repository, stable value of user service, and we create empty slots for these. And here is how we create them: orders, compute if unset, and so on. Okay, so that's a big step forward, but I still don't really think this is perfect, because we have this kind of invariant delay that we have to go through a different method. And when we declare the stable value here, the recipe is somewhere else in the code. They are not kept together. So I think we can do even better. And in fact, a stable value offers more than just a stable value holder. It offers stable function and stable collections. So for example, we have something called a stable supplier. So I can say that, wow, here is the supplier of logger. And if it's not set, here is the recipe for it. And then I can declare that upfront. And then I can just, refer to this logger get method here. And I can get away with this invariant that I had to go through and use every time I use the logger, I had to go through this special method. So I can now refer to logger directly. And as you can see here, no, not here. Get is the only method that is here, and that's the usual suspect of synchronize and wait and all that method. So that's the only thing I can do with the supplier here. And even better, when I go to my application, I can say that here is my order, and here is the recipe for that. Here's my product, the recipe for that, and the user server, the recipe for that. And they are only created when they are needed. So I think now we can try to run this application here. So let's see. Yeah. So I restarted this, so therefore it's using another Java version. So I will switch to the correct Java version, and boom, there we are. So we can see that it at least works. And we will see later that it actually is performant as well. So that is great. But can we do better than even still? And I think, yes, we can. So suppose we have now an application that wants to shard and have a lot of order controllers, not only one, but have a kind of a collection, maybe 16, a pool of these order controllers. So then we have something called stable collections. So I can say that I have a stable list of a certain size, and here's the recipe to create every element. Every time I first refer to an element, this lambda here or method reference be invoked, and the value will be inserted into the backing underlying stable value, and the VM can constant fold this once it has been set. And here is a simple way to kind of load share. We take the thread ID and then we just, order pool get and that index. So if I would have deployed this application in a single thread environment, only one order controller will be able to be created. They will not be created upfront. And this is very good indeed for the startup performance. Okay, so this is the kind of overall way that stable value works. Now I will go to kind of another section where I show how you can apply stable values in your kind of typical idioms. So one of the idioms is a singleton. I know that people debate, is singleton good, is singleton bad? But anyway, we have a lot of singleton, and here's how you can do them with stable values. So I have a singleton up here. I haven't implemented any logics around it, but I just want to show how to do it. So I have something called a singleton supplier. I say that I have a stable supplier, and here's how you create it. And then my get instance is just singleton supply get. And every time you refer to get instance, the VM is able to constant fold the value of my singleton and use that singleton directly. I don't have to actually, invoke this method, invoke this get, go to the supplier and do all the internals. So I will get kind of a full speed here. And you can do more obscure things. Maybe you want to implement a tringleton, which only contains 3 of your stuff. And then you can say that I want an int, a stable int function with 3 valid inputs, 0, 1, and 2. And here is my recipe for how to create them. And then my get instance, I can have an index, and they will return. And then if I have my get instance 1, will be constant folded, and just point directly to that tringleton that you selected. So that's cool. Another thing that is very common is that we have a non-evicting cache. What I mean with non-evicting is that we can set the value, and once we set it, it will be there forever. So in this example, I have a very simple example. I have a square root cache. It might not be sensible to ever implement that, but you can easily think of other solutions where we go out on the internet, pull down the content from a website, or we are computing something much more. Maybe we have like a prime factorization or something. But here I said that I have a stable function. Now a function is the most general stable functions that there is. And I say that for the values 1, 2, 4, 8, and 16 here, which are powers of 2, I have that's the valid input of the function. And here is the value of the function. And I can also, elect to have a map, which looks very much the same. Now, a stable function and a stable map is very similar, but the map is more, extensive. You have this size, you can have the iterators and all that stuff, and it's very useful if you want to interoperate with the old code. So that is the difference here. And then I can say square root cache apply 16, and the JVM will constant fold this value to 4. So it will be equally fast as I would have written square root 16f equals 4. It's the same performance after it had been set. So here is a more demo-friendly kind of solution. I think all of you who went to the computer science class have seen this example here. We are going to compute the Fibonacci delta series, which is if we have the value 1 or 0, it's the same value, 0, 1, but otherwise it's the sum of the 2 preceding elements. So here we have 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. And of course we can, very easily set up a recursive solution for this. So if I is less than 2, it's I we return. Otherwise we return fib of -1 and plus fib of -2. And as you can see here, this is recursive. And it turns out that the complexity of this method is exponential. So the growth in time will grow exponentially as you increase your value. So we can try that now. We can try and run that here. So let me do that. I have Fibonacci here, and I will enter 45. Now, incidentally, 45 is the highest value I can use because I've used int representation. So let's run that now, and it's very slow. There we have the first value. There's the second value. But stable value can come to the rescue here. So, and of course, I must show you that, of course, this has a turtle. But if you use stable value, you get this rocket here instead. And why do we get a rocket? You will see. So instead of doing a recursive call, we can say that we have a stable list of a certain size. 46 is the biggest we can have as an int. So we say that we have a stable list with 46 values. And the way to compute this element is to invoke the Fibonacci function. And if we go to the Fibonacci function, we can say that, well, if I is less than 2, then it's I. Otherwise, we refer to the list here. So this kind of gives this chain invocation around the lambda here and how the lambda is actually throwing back results on us. And the VM and StableValue is actually capable of figuring all this out and still be able to constant fold the values for us. So we can run this as well. And I think you will notice a significant performance difference. So there we are. It just exploded. So actually this will turn the exponential order exponential to order n the first time, and the second time it's order 1. So this is just working with constants. So if I were written, for example, fib 6, it will constant fold to 8 once it has been computed. Okay, so let's head over here and do some performance tests. I have prepared a performance test, but of course it takes some time. I will start it now, and then only then go back to see how this looks like. So I will, take this value here, bring up the class. There we are. Okay, so I have 3 benchmarks here. The first one, it's only going to return a constant. I think it's hard to imagine something quicker than just returning a constant here. The constant is unsurprisingly 42, and that has been returned by this method here and consumed by the JMH network framework. Then I invoke a double check locking idiom, which I've actually implemented what I just showed you a few classes ago when we do this double checking here. This also provides for null safety, double checked locking. And then we have stable value. In this case, it's the stable supplier. And both the double check locking uses this lambda here to create the constant, and the supplier also uses the same lambda here. And now let's head over and see where we are. We are not finished yet, so we need to wait a while, I'm afraid. Okay, and I'm running this a few times, and let's head over and let's wait. It's 30 seconds left. So it's going to be very exciting, and then I have time to take a refreshment while we are waiting. "15 seconds. The judgment is close. Is this going to work? There we are. So we can see that on my computer, I'm running a Mac M1. Returning just a constant is 0.8 nanoseconds, whereas calling the double check locking is twice the amount of time. And stable supplier is equally fast, I would say. It looks like it's faster here, but I think that is within the error margin. So this shows that stable value is equally fast as returning a constant, even though we have the flexibility of initializing the value when we want. So therefore, I will go back to my slides again. Let's see here. So if you only remember one thing from this presentation, this is what I want you to remember. So we have mutable fields, which you can update any number of times, 0 times or 1,000,000 times. You can update a mutable field from any location in your code. It doesn't provide constant folding because it can change at any time. And you can do concurrent updates. Of course, you have to be careful, but you can do it. Then at the bottom, we have immutable or final fields. They are updated exactly one time, not 0, not 2 times, but always exactly one time. And they can only be updated in the constructor or class initializer if it's a static field. And they support constant folding, but they don't support, obviously, concurrent updates because it's not possible to update them from any places than in the constructor or the initializer. And then now we introduce a new kind of field type, I would say. So we had final and non-finals ever since Java 1.0, but now we have a middle alternative, which provides us almost all the benefits from the two of them. We can update it 0 or 1 time. That's the restriction. We can update it from anywhere in our code. We get constant folding, and we can update it from different fields. So I think this would be a perhaps larger addition to Java than you might think from the beginning. Okay, and here is the benchmark visualized. So you can see the constant and stable value is about the same. Okay, so what's the secret sauce? How is it possible to do this? Well, a stable value wraps the underlying data is annotated with an internal notation called stable. And that is something we have used internally in the JDK for many years to improve performance. Unfortunately, we cannot expose this because that will entail security risks and consistency risks. But StableValue offers a safe wrapper around the stable. And we are ensuring the invariant that we only update the value at most months using compute and set. So this means that the thread that succeeds with the compute and set operation wins. We also are very careful to have this kind of transitive trust. So we have something that has a stable value. Everything that we declare must be in a chain of trustworthiness. So if it's a stable value, it can refer to another stable value, but it can't refer to a mutable field, for example, because then the trustability is violated. And the VM treats stable value and stable arrays of stable value in a certain way. It's very difficult to update a field that's been declared with stable value. It's equally difficult as to update a field in the record. So you can say that stable values and stable value arrays get the same kind of properties that a field in a record does. And the versatility of stable value will become even better when all final instance fields will become trusted someone in a later VM. Okay, stable value summary. Codes like lazy initialization, but performs like a constant. That's the battle cry. It's transitive. So if we have maybe a logger usually has some kind of is-enabled function. So if we have order controller.logger.is-enabled and that is false, then the VM will be able to constant fold that false, and it will be able to see that maybe I have if logger is enabled and then I have all the logging, then it's able to actually remove all that code for us. And that will improve not only performance, but will also make your code more efficient and more dense, so to speak. Okay, so it provides stable values, stable function, and stable collections. And it might come to a JDK near you soon. I hope it's going to be in 24, but I can't guarantee that. Okay, so I think we can take some questions now before we go over to the other part. It's difficult for... Yes, a question there? A good question. So why haven't you used lazy keyword? And the simple answer is that we have used the lazy keyword. That was one of the naming candidates in the beginning. We named it lazy, we named it computer constant, and we named it a lot of other things. But we realized that stable value was more kind of descriptive and would fit better as a name. But it is an incarnation of something that is lazy. In fact, laziness and deferred immutability is more than laziness. Because if you have something that is lazy, that means that you can initiate it later, but it doesn't say how many times you can initiate it. Whereas deferred immutability says that you can only defer the immutability. So they are not kind of really the same thing. Okay, more questions? Yes?
How do stable values relate to gap to your fee intrinsics for LDC?
Yes, that's something we thought about, and we thought about how can we integrate them. But at the moment, it's this. It might be a tighter integration in the future. So it might be the case that the lambdas you are seeing now are, under the hood, is creating a new class. But it's not. It doesn't necessitate that. It might be the case in the future that we are using more clever ways. So maybe it will in the future. Okay, yes, question?
If you said it is initialized with computed swaps, so there is still a risk of the initialization function running multiple times for single value, is that right?
That's a good question as well. So the question is it possible that the initialization logic is run several times even though just one wins? Is that correct? And the answer is that stable value guarantees that the provided lambda is only invoked once. That's a guarantee that you get. And so if there is another thread wanting to do that, it has to wait until the computation is ready. Okay. Yeah, more questions? Yes?
Yeah, so you said that the constant folding is transitive, right?
Yes.
So if you have a stable value of random on which you call next int, is that constant folded as well, or like, you know, when you're doing stuff that depends on the internal state, or if you do a constant fold of an atomic integer and you call get an increment, you only get the same value forever?
Okay, that's another question, and it's kind of related to a question I thought I would get. So stable value is only shallowly immutable, so it doesn't, flatten out things and make the underlying stuff immutable. So the question is, if I, for example, refer to an atomic integer, then only the reference to the constant, the atomic integer will be constant folded, but not the atomic integer itself. So therefore, the transitiveness ends there. There is a boundary of trust, and it stops there automatically. More questions? Interesting. Good feedback. Yes? So I guess the question is, why didn't we use a language feature? Why didn't we have a keyword? And that is something that we have thought about as well. Actually, there is a draft JEP for exactly just that. But it's like adding something to the language is more work. And just doing a library implementation is easier. So we haven't really outruled that this will, emerge in another incarnation with the language feature. So I guess that is the answer to that question. Okay, more questions? Good questions. Yes?
A follow-up on the transitive. So if you have a stable value that returns a stable value that returns a stable value, is that transitive invocation constant folding?
Very good question. That's exactly the question I wanted to have. It's almost like we spoke before this. So the question is, if I have a stable value that refers to another stable value that refers to a third stable value, and so on, is that constant folded? And the answer is yes. It will actually constant fold them all the way. And that is great, because I think as people are going to pick this up over time, it's like a central station. The more trains that goes there, the more beneficial is it to get more trains there. And it's the same with stable value. The more the usage of stable value picks up, the more the benefit of stable value is. So I think we're going to see stable value being used for example, for logger providers or Spring components or whatever. And then we will just flow through all the stable values and constant fold the value. And our application will run much, much faster and more energy efficient than ever before. Nice. Good question. Anything more? Okay. Yes?
What about naughty reflection things like setting things accessible? Can you update?
Now we are on the edge of the scope of this presentation, but we can go there actually. So what we did was that you can't do set accessible true and then update the field. That will throw an exception. Just that it will do if you do the same thing in a record. You can't get the offset for the field using unsafe, because that will throw an exception. But there are ways to do it, but I will not tell you how. Yeah. Okay. Good. So let's continue. You can come back with more questions later. So that's that. Let's look at segment mapper just shortly here. So I will go over again to my IDE here. And I will pull up memory segment. Now, memory segment models a 64-bit region of memory. You might be aware of byte buffer, but that you can only use an int as an index. But whereas for memory segment, you can use a long. And so you can address terabytes of data. And if we go in here, you can see that we have get operation for numerous, float, long, double, all the user suspects. And also, set operation here. Set operations for the same set long, set int, and all that stuff. But there is no, set a record or something like that. So let's just pull up a demo where I have the all familiar record point X and Y here. So this is a record, and I can say that I have a segment that contains coordinates 3 or 4 here, where presumably 3 is the X coordinate and 4 is the Y coordinate. And then I create a new point by extracting the Java int at offset 0. And then I take the segment, extract a Java int on offset 4. You see, this is all manual here. And then hopefully if I print this value out, I will have a point with the coordinates 3 and 4. And then if I want to set a point, I can create this new point here. And then I can manually extract the X value and set that at Java int position 0. And then I can set the Java int at an offset 4 for Y. And then if I print this using this utility method I'd created, this segment will contain 6 and 8. And that sounds great, but you can all imagine how things will turn to the worse if you have a line that has a point that denotes the beginning and another point that denotes the end. And then you have a group of such lines in a list. And then you have a drawing, which is a list of groups. Imagine coding that manually. It will wreak havoc on your code base. So what we can do then is that we introduce something which is a segment mapper. And a special case of a segment mapper is a record mapper. There are other mappers that you can map for primitive types, but I will focus on the record mapper today. And basically the record mapper has 2 operations. It can get something of this type from memory, and it can set something in memory of this type. Very simple. So we will see how that works in our demo 2 here. Just let us run this first example first. So I have it somewhere here. So I have the demo here. I run it, and yes, it works. It produces a point at x equals 3, y equals 4, and then we set the value, and the value of the segment is 6 and 8. So it actually works, even though it was quite tedious to write the code. But why don't we use this instead? We have an array of the value 3 and 4. Then we have a factor here, say record mapper of this class point. And then we have something here, which is a memory layout. And let us show what is a memory layout. A memory layout is something very similar to a struct in C, or can be very similar to a record struct in C. So I see I have a struct here of an element which is an int with name x, and I have another int with the name y. And of course you see that because point is a named tuple, the names here are actually a part of the API. I can match this x and type int with this int and type x, and y is the name here with this name y here. And then I have everything I need to construct, to reconstruct and construct values of this type back and forth from memory. And that is what the mapper actually does for me. And it will create a performant mapper when I provide the class and when I provide the layout. So it will do all this matching, checking the types, generating code, and there we are. So now I can use my mapper here and just get this point from memory at this offset here. And this hopefully will get me point 3 and 4. And you see that this is much simpler than before. And then if I want to set the value, I just invoke set segment 0, and I just create a new point. And that will be written to my segment. And if we look at the more contrived example here, we have lines. And a line is actually another struct of a point layout with name begin and a point layout with name end. And so I can ask for another mapper that maps to a line using this layout. And that will be created automatically for me. So now if I have a segment with a point here and another point here, I can just use my getter here and get a line. And then I can print the line here, and then hopefully I'll get something like line with the beginning point x equals 0, y equals 0, and the end is a point where x equals 3, y equals 4. And the same if I want to set the value, I can just set line segment, and I create a new line with this begin point and this end point here. And hopefully this will print something like 10, 10, 13, 14. And groups the same. A group is just a sequence layout with maybe 10 elements of line layouts with lines. And you see how nicely this composes rather than I have to explode my code and explain all these kind of dependencies. And I can even go further down here. So let's run this example here. Oops, demo 2. And we can see that it actually works. So I can retrieve my point, I can get the line, and I can update my value, and there we are. So I think this will provide a very useful tool for working with flat memory. And I hope you saw Victor and Brian's talk on serialization and New Hope, where we had you can separate the concern from serialization and abstraction. And then I think that you can use, if you want to send things binary on the wire, you can use the record mapper to create such efficient transport means if you want to send those serialized objects over the wire. So I think that will click very good into where we are seeing Java heading in the future. Okay, so that is that. Okay, turns flat memory into structured memory. It's composable. And it actually hides more gems than I can show you today. We are working on some very cool extensions of this that we haven't really thought ready for yet. I'm not ready to share them because I think that they have some drawbacks. So I want to polish them a little bit more before I show them. And I think this will appear in the mid-20s. That is quite soon, but maybe next year or so. Okay, so that was what I have to say today, and I will thank you today for showing up and asking all the good questions. Thank you. And if you have more questions, you can ask them now. Maybe for segment mapper, we haven't had any questions about that. I'm hoping the Mr. up there who asked all the nice questions had some clever question about this, but he's shaking his head. Okay, it was free. Yeah?
So why do you have to manually declare this layout if they have to match up with the type and the name of the record?
Good question. And the answer is you can generate them. The question was, why do you have to have this layout? Isn't it obvious that this class is going to have a certain layout? And yes, we are working on something that's called a natural layout. So you can, if you have a record, you can ask for the natural layout of that record, and then you can just provide a class. So you assume that it will have this layout, which is natural, and then you don't have to provide the layout. So that's a good question. Okay, more questions on that? Yes?
You have named your parts of your layouts according to the fields in the record. Is that mandatory or is it convenience?
So the question is, how about the names in the layout? Are they optional and so on? And the thing is that if you provide a layout, there must be a mapping for every component that appears in the record class. So if you have a record class int x, int y, and then the layout you provide must provide something that is of type int that has the name x, or has the name with y, and is of type int. Otherwise, you will have an exception when you ask for your mapper. Yes.
Can you transpose them then? So if you have x and y in the record, you have y and x in the struct?
Yes, another good question. So if you want to, swap them around, and you can just say that my x is on the other position and my y is on the other position, will that work? And the answer is yes, it will work. So it's not dependent on the position at all. It's only name. You might have a long list of various things in your struct with x, y, z, color, opacity, whatever you have there. But I'm only interested in x and y. And then you can do it's like you can say it's some kind of pattern matching, but not really. But you only have to provide what you're interested in. So that is the answer to that. Okay, more yes.
So the segment mapper, how does this one work compared to the value classes with Valhalla?
Okay, so the question is, how does this work compared to the value classes with Valhalla? I think that it's like, it has a similarity because you can pack things very densely. So you can have, for example, a sequence layout of points, and then it will flatten that out in memory. So in that perspective, it's similar to Valhalla or the objectives of Valhalla, but it's like here you do it explicitly. You have to define it for yourself. It's nothing that happens under the hood. So here you can do an explicit flattening. Yeah. Okay. Thank you ever so much, and I'm available here if you want to ask questions in person. Thank you all.